Hey everybody, welcome back. Today we're going to be talking about screen space shadows. Now the first thing you're going to notice if you're used to my other videos is things are a little different. The reason why is because all the setup and prep work that I normally do for my videos takes a great deal of time. I like my stuff to look really professional, but it's also meant that I haven't really done videos for a bit because of the amount of workload that goes into it. So I'm kind of scaling back today because I really want to get this out here. I think this is a really cool technology and I don't want to have an excuse for not putting this video on the internet for you guys. So we're gonna do it the the more nitty gritty raw way today. So hope you'll forgive me for that. All right, but again, like I said, we're going to be talking about screen space shadows today, and so I'm going to be using Godot for this. But what kind of got me into this was I was on YouTube, and people are talking about the Callisto Protocol, which is a really graphically amazing game, and the characters in it just look phenomenal. They look pretty close to photorealistic, and I was just really amazed by it because it's such an old game now. It's like a decade old, I think, or what have you. And I just found that really graphically impressive that a game so long ago could just have that kind of fidelity for graphics. And there are a lot of other games that are like that too. And I kind of just was analyzing the facial structures and the rendering of that, trying to figure out what made the characters stand out. And one of the things that occurred to me was that the shadowing had a great deal of influence on how realistic a character looked. In fact, I'm going to go ahead and pop a picture up real quick so we can kind of have a look at it. So yeah, basically, screen space shadows work over irregular surfaces, and you can kind of see that happening here, which is kind of a cool thing. Now this whole character has a whole lot going for him. I mean, you're not going to get this out of the box in a lot of graphics engines. First and foremost, I heard Callisto Projects actually using their own BRDF. I kind of looked into it, but for the moment, that's a little bit beyond me. So not something I'm going to focus on too much. Another thing this character likely has going is subsurface scattering, which kind of deals with how lighting deals with like skin surfaces because it doesn't work like a plastic or a metal. It has its own different way of doing reflectivity. I actually have subsurface scattering going on in my character right here. It's kind of a crude version of it, but it works really well, and it's definitely better than nothing. In a future video, we might talk about that, but for right now, I really wanted to work on screen space shadows, and the reason why is because they're not terribly difficult to implement, and they create a massive amount of realism for irregular surfaces. I mean, the shadowing in the eyes over here, the shadowing underneath the nose, the shadowing at the lower lip. We also have some shadowing in the ears over here. All of this is accomplished probably through some form of screen space shadows. And the problem that we have with other shadow maps is basically like typical light shadow maps you would get in like Unity, Godot, Unreal, things like that, is they don't typically have the resolution to really affect these sorts of areas because remember your shadow maps have to deal with a large area of lighting and you only have a finite resolution. So if you're using 512 by 512 or even a 1 or 2K, getting fine areas like the eyes is going to be very difficult for it to do or to at least do correctly effectively, I would say. So what we're going to do is we're going to offload that workload onto our own spatial shader. And that way we'll have direct control over it and we'll be able to do it on a per pixel basis instead of a per texel basis. And hopefully we'll gain some performance off of that. So as you can see on the left over here with my character, there's a stark difference between the two. Yeah, let's have these both up at the same time real quick. So with her, there is no nose shadowing. There's a little bit of lighting on the underlip or shadowing under the underlip here, but it's not really casting. It's more, I think, just a form thing going on. There's really nothing going on as far as shading inside the eye area. These are in stark contrast to. Oh, I didn't know I could do that, but just how the lighting works in this case, and it just looks so much better in Callisto Protocol. So again, I'm not going to be like making my character look like a Callisto Protocol character by any stretch of the imagination, but I would like to see how close I can get her to looking a bit more like this at least. And so we'll go through that and I'll show you how it works out. So we're going to be using a ray marching system, I think I said. And, excuse me. So, ray marching is going to be a little costly in performance, but it shouldn't be too bad. We're going to try to keep it as simple as possible. And you can always tweak the values to whatever works best for your particular scene. Now, again, screen space shadows work best on irregular surfaces. The human face is a perfect example of that because we have inset eyes, we've got a nose that bulges out, we've got lips that bulge, stuff like that. Anything with that kind of a topography works really well with screen space shadows. So another example that's non-human might be rubble on a ground, or dirt and rocks and stuff like that that actually are modeled on the ground. That you could have those cast shadows using this sort of method. Another thing is we are not going to be implementing this as a post-processing effect. You probably could. I don't see any reason you couldn't. But we're actually going to do this as a spatial shader, and that way I can make it to where it only affects certain materials. And in this case, I only want it to focus on human skin right now. So her armor or anything else in the scene won't be affected by this. And that should help keep the processing a little bit better as well. So we're not worried about rendering subsurface, microsurfaces and stuff like that in areas where there really aren't a lot. We don't need to waste processing on that. So this really centralizes the effect, which is super important for keeping your performance in good shape. So, all right, let's get started on this bad boy. Again, as always, going to be using Godot for this. It's all math, so you could pop it into Unity or Unreal or even your own custom engine if you want. There shouldn't be too much problem. But since we are using Godot on this one, we do have to get this set up properly. So first you want to create your own shader, obviously. We need to, what we're going to need to do is we're going to have to set up a depth texture for this. And you're going to want it, you can call it anything you want. We're going to call it depth texture for this. The biggest thing is you need to make sure it says hint depth texture, or this will not work. This tells Godot that it's going to be using the depth buffer as a texture. And we're going to look into that for doing our ray marching. I've got some other things over here. So there's repeat disabled and filter linear. I would also put those on as well, but they're probably less important. The repeat disabled is probably more important than the linear, but yeah, do whatever. Anyway, actually, we could probably even make it a point sample now that I think about it. But anyway, the point is, get it set up like that. The other issue, though, is as soon as you introduce a depth texture into your shader, you immediately go off the opaque, and now you're in transparency land. And that can cause some really weird artifacts to happen. So to correct for that, make sure you have a render mode, and you want to enable depth prepass alpha. This will cause the depth information of the mesh to be written before it does any of the fragment shader. So it basically corrects the depth buffer problem is what it does. So make absolutely certain you have this on. If you notice that your character's face is just doing really wacky things during rendering, you probably forgot this. So go ahead and do that. All right. So before we get too far into the code real quick, I do want to kind of showcase what the end result's going to be, and then we will talk about how we get there. So again, this is basically kind of uncanny valley land because since she's not casting shadows, our brain is having to kind of like add that information in, and it's causing our mind to work too hard to recognize this as a face. Turns out our brains actually recognize faces not just off the structure, but also off their shadowing. So if I enable screen space, it's going to end up looking like this. And there we go. Now we have hard screen space shadows. And as you can see, it's just, for whatever reason, your mind just has to process the face less. Having that information inside the shadowing inside the eye socket area, the shadow cast from the nose, and the shadow cast from the lower lip just really adds a whole lot of detail that helps our brains recognize this is a human face. We need that information. And so I consider it pretty critical to have this kind of a shader in your shader arsenal. And we're going to get closer to her. I hope it's not like too uncomfortably weird, but there is a reason for that. So the biggest reason is, like I said, this is the hard variation. And so as you can see, it's kind of a pretty coarse line over here. If you're doing something that's more stylized or something that kind of goes into the direction of cartoonish or whatever, this is probably all you need, and you'll be pretty happy with this result. If this isn't enough for you, then stay tuned because we're going to take a modification of this to actually smooth this out. And it's virtually cost free. So it's just amazing how you can get a nice, smoother edging, some blurring going on over here that makes it look even more realistic for photorealistic results. It's very little modification and very little. Actually, I don't even know which one's faster, to be honest. They may run at pretty much the same speed. So pretty awesome. But let's go ahead and get into it. The one thing I will say is I'm going to be doing this inside of an include file because I want to be able to reuse this in other shaders. You don't have to. You can put all your shader code inside whatever shader you're working with at the moment. This is just an efficient way to reuse shader data so you're not reinventing the wheel. So anyway, mine's in here. And what we have is we've got, well, first and foremost, we've got a couple of utility functions. I may or may not talk about these. We'll see how it goes. Effectively, if you want to learn, or if you need this information, here they are, so you can copy them down. You're going to need them for the shader, so make sure you have these written down. Pause the video if you need. But effectively, we're going to need to take a position on the screen, so screen UV, in a vector 2, use an inverse projection matrix, and that's going to give us back the... Oh, and we're going to need our depth texture also. And this is basically just so that we can get the depth of an arbitrary pixel on the screen at any given time. So I can basically look in using screen UV and just be like, hey, where is this pixel in depth? And then it'll give me the actual 3D position of it. We'll just be taking the Z of that value because we don't need the X or Y, but it will give you the actual position of the object, or of that pixel in view space. Sorry. And this will effectively do the opposite, where we essentially have a position in view space, and then we can project it into screen space effectively. And again, I'm really not going to get into these too much. The information, like how these are set up, how they function, stuff like that, these functions are all over the internet. If you look these up in Godot and Google or what have you, you're going to find pretty much these exact functions all over the place. So we need them as utilitarian functions so we can get our stuff to work. But let's go ahead and check out our screen shadows, and we're going to do the hard one first. And so, yeah, basically, before we jump into this, I should also probably explain how we're going to use this. So let's go back to our skin shader real quick. And so what we're going to do is we're actually going to overwrite the lighting system. So in a spatial shader in Godot, you're probably used to having a vertex function and a fragment function. You may not know there's a light function, but there is. And the light function actually allows you to override the lighting system. So if we're going to go down here, we have light. And I'm doing a whole bunch of stuff with GGX and all that, so you can ignore all that. But the biggest thing that we're going to end up doing is we are going to call our screen shadow, and it's going to give us back a screen shadow value. And that value is going to be a value between 0 and 1. 0 means that it is completely attenuated, or basically it's shadowed, it's occluded. And so there should be shadow there. 1.0 means it's unoccluded, and therefore it's getting full light. Any value between those two is going to be some fraction of those. So, 0.5 would be like half lit. This value is intended to be multiplied along with the attenuation value. So an attenuation is a special constant you get, like light and light color. So the resulting value of our function should be multiplied by the attenuation to get the final result. And that's basically how that's going to work. So getting back to this, for our screen shadow, we are going to need our depth texture. So I'm going to pass that in as a parameter just to make life a little bit more flexible. We're going to need a source position in view space. That's going to be the position of our pixel, effectively. And we're also going to need light. This is actually the light normal, or the direction the light is going, because we're going to basically be predicting or casting photons along the light's normal to figure out if the light is, or if the particular source pixel done by source position, if it's occluded or not. So we're just basically going to be ray marching to backtrack along the light direction to see if there's anything occluding. We're also going to need our projection matrix and our inverse projection matrix. Those are going to be used for here. Same with the depth texture. And then finally, we have an intensity value, which basically you could kind of ignore that for now. it's going to do some trickery that'll basically, not trickery, it's going to allow us to basically say how much we want this effect to apply or not. And for the hard shadows, I don't think it works right. So yeah, it might be a little broken. You can test it and find out, but it wasn't really designed for this particular effect. It was actually designed for the smooth effect. So, but for now, we'll just kind of ignore it. Let's get to the meat and potatoes. So the first thing we're going to want to do is we're going to define our result. And this is going to be the value that eventually will be multiplied by the attenuation inside our light function. Then what we're going to do is we're going to start ray marching, and that's what our for loop does. And we're going to do this 50 times. You can do it however many you want. Probably best if this were a constant, like a define or something that you could actually change. But essentially, you're going to want to pick a value. Higher values mean it's going to ray march longer, and that means you're going to have a performance issue. So you want to keep this value as small as you can, but smaller values can also lead to degradation in quality or clipping in the shadow. So find a number that works great for what you're doing and run with that. Okay, that's pretty much the beginning of the for loop. We're just ray marching. So now what we're going to do is we need the position of the photon as we're ray marching. So that's what we're going to call light position. So we're going to backtrack that photon towards its source. And so how we're going to do that is we're going to take the source position, and then we're going to apply the light normal, and we're going to multiply that times I, which is our current step within the ray march. And we're also going to apply a step value to that. So this value should be really small, by the way, because we're dealing with really tiny movements. Obviously, this is we're dealing with like the distance from here to here. That's really small. So we want to make sure this value is really small. But you can adjust this and see what works out with it. In fact, this can probably be better optimized. I just haven't done it. All right. So that'll get our light position as we're ray marching. And then what we want to do is we need a test position. So the test position is also, it's going to be the pixel underneath the light in view space. So this will be a 3D value just like the light position, right? Okay, so how we're going to do that is we're going to start by projecting the light position against the projection matrix, and we're going to take that result and we're going to feed it into the pixel position. So we're going to screen space with the current light position, then we're going to go back to view space. But rather than just getting the old light position back, we're actually going to project this against the depth texture to figure out what the pixel underneath the light, what its actual position is. So this won't actually give us the photon position. It'll give us the pixel position underneath the photon. And all we have to do then is just simply check to see if the z values, the difference between the z values, to see if the light position is beyond the test position. And if it is, then we're occluded. And if it's not, we're not occluded. And so we basically just keep on doing that until either we hit all 50 of our iterations, at which point we're not occluded, or this fires off and we did find something that's beyond or that's in front of our light and we did occlude. And so this will basically just set result to 0 and break. And then again, you can kind of ignore this code. The really important thing is just really result. We just basically return result. And that will give us either a 0 if we're occluded or a 1 if we're not occluded. So this function will always return either 0 or 1. And that's it. That gives you your hard shadows. So pretty cool. Not too difficult. It's basically just 3 functions. You can probably write this up in 10 minutes. And you've got yourself some material-based screen space shadows on a spatial shader. Awesome. So now let's go back here and let's see what the difference between hard and soft looks like. So if I turn this to soft, you'll see now that this area just softened up tremendously. So let's go back. Here's hard. And here's soft. So you can see there's nice gradient between the two. And so the question is, how do we get that? The answer, fortunately, is pretty simple. Because what we're getting is when we do the Z check between the light position and the test position, if we simply subtract those values or get the difference between those values, that will give us a shallowness result. So effectively, if the light position or the light position Z and the test position Z are very close together, that means that it was a grazed light hit. If they're really far apart, then it's a very strong hit. And so what we're basically going to do is just simply return that difference instead of just either on or off. And we do that in here inside the screen shadow soft function. Uh, One massive difference right here is that we're actually setting result to 0. So make sure you change that because it sets to 1 here. That's very easy to miss. Other than that, this is pretty much the same algorithm. All of this is the same. The only thing that changes is right here. We're no longer doing an if statement. We're grabbing the difference between the two. And so now, once we get that, we're going to multiply this by some value. This kind of hardens it out, and it provides where most of the occlusions are going to be strong occlusions. And then as it gets kind of further away, just on a small line, it's going to end up gradienting out a little bit nicer. And that's controlled primarily by this value. So adjust that however you see fit. And then when you're all done, since we start at 0, that means all of our values are at least 0, possibly even smaller than 0. So that would be negative. That's a massive problem. So what we want to do is then we want to multiply our end result by, we want to add 1.0 to our end result to bump that back up into non-occluded space, we'll call it. And then that's basically it. Once we're done, we just return our result as we did before. The clamp on this is far more important because our values might be significantly below below 0 now. So you probably have negative values. So you really want to clamp that off to make sure that you get a 0 value for this. But other than that, yeah, that's it. And again, all the intensity is doing is basically just setting how much the effect is prevalent. So I can set that value to 0, in which case you'll get no shadowing. And if I set it to 1, you get full shadowing. That's all it works for both of them. Again, it might be broken on the hard one. You'll have to test that. But that was what it was designed for. And that's essentially it. You now have your code for screen space shadows. Enjoy. I think they're pretty nice. So let's go ahead and have a little bit of a test here. So if I run over here, press F6. We'll have a quick look at how they look in an actual game. So real quick, yeah, there we go. Looking pretty nice. So you can see the shadowing underneath her nose. Not so much under her lips, but I think I can see a little bit definitely around her eyes, which is pretty cool. And there are some spots in here. By the way, the ship is designed by somebody who goes by the name Vattalus. Fantastic work. I absolutely love it. This is all rendered in Godot. And sadly, he only does work for Unity and Unreal right now, but you can convert his ship to Godot. It just takes some work. Definitely set out a weekend or something for it, but you can get his ships in Godot if you put some effort into it. All the texture maps, the materials, all that kind of stuff are set up in such a way that it works great with Godot. So definitely have a look. I'll throw a link to the ship in the description so you guys can have a look at it. I think you'll love it. But anyway, here's a room where I get some pretty striking lighting. And as you can see, the shadowing on her eyes, on her nose, all of it's looking really good here. Another cool thing, too, this is actually something I totally forgot about till just now. These lights actually do not have their shadows enabled. However, if I get close to one of these enough. Yeah, you can kind of see it here. Let me kind of fiddle with her angle just a bit. Yeah, you can definitely tell. Come on. Yeah, there we go. You can kind of see at her nose and everything. We're still getting shadow maps. Not shadow maps, rather. Screen space shadows for her. Off of these lights, even though they're not set up with shadow mapping. The reason simply is because we did it on our own shader. This has nothing to do with the shadow maps at all. They're completely independent from light shadow maps. So that's pretty cool. You basically get that for free, which is kind of nice. And that's basically it. I think the end results speak for themselves. I highly recommend adding this to your shader arsenal. Having this inside your games in select areas can really benefit the quality of your work. As you can see too, like I said, we did this on as a spatial shader for material. Only affects her face. None of it's happening over in the geometry outside of here. You could again make a post processing shader that will do this for your entire scene, but that would be a lot of computational value, and I really don't think it's necessary. But doing it on your characters' faces and maybe some select objects within your world would have an amazing quality boost to your game, and it wouldn't have that big of an effect on your performance. So this is really great stuff. I hope you enjoyed it. I have no idea when I'm going to be posting another video again, but keep your eyes open for it. If you made it this far and you really liked what you saw and you plan on implementing this in your own engine, or you just found it interesting, consider giving this video a like. And if you want to see more of this type of content, because I do a lot of stuff involving game development and game creation, consider subscribing. And again, hope you found this useful, and I'll see you in the next one. Have fun.